general basics to help you understand what echolocation is. You'll see the parallels later on in the lesson. Sonar stands for sound, navigation, and ranging. So that acronym doesn't include all of those letters, but you can see how it's developed. It is a method of navigation involving the propagation of sound. In other words, the way that sound moves through the water. Sonar can be used to both measure distances and build digital images of surroundings. Especially with submarines that are very deep underwater, it can be very difficult to see in a dark environment like that. So digital images that are computerized are necessary for submarine crews to understand what their environment looks like. Sonar exists in two forms. It can be passive or active. In its passive form, sonar works by detecting noises emitted by other vessels or objects in its surroundings. In the active form, it works by sending pings and listening for an echo. In echolocation, active sonar is the method of sonar most parallel. The amount of time that it takes for an echo to be received combined with the properties of sound can allow a sonar system to gauge object distance and water composition. So in other words, it can just build a picture of like what the surrounding is like, how far away objects are, what's in the water, how far away those things are. And applications are available for many fields. For science, while sonar can be used for wave measurement, water velocity, and sub-bottom profiling, which is the job of oceanographers to know what the sea floor looks like, because we can't see all the way down there with our eyes. The applications for the civilian industry are fishing and remote controlled vehicles, like, for example, diving. When they examine the wrecks of ships like the Titanic, they can't see all the way down there. So they can use remote controlled submarines to look down there for them, and sonar helps those machines navigate. And applications for military are probably the most well-known widespread, namely anti-submarine warfare, which is ASW for short, detection, torpedo guidance, minesweeping detection, underwater communication. Minesweeping is essentially the practice of detecting mines, which are like proximity bombs that explode when ships pass through an area, so that you want to deny an enemy the ability to ship whatever on boats through an area. And in minesweeping, sonar can help detect those bombs so that they can be diffused or the problem can be tackled. Underwater communication can also be harnessed with power of sonar. And again, sonar is going to be covered extensively in the next session. So echolocation, as I mentioned before, is described as nature's own sonar system. Echolocation is a natural form of sound navigation, distance gauging, and location that is biologically supported by many species in different environments. Actually, humans can even use echolocation just by, it's rumored that a lot of blind people, it's hypothesized that blind people can develop a form of human echolocation to be able to understand what their surroundings look like. Without their eyes, they can just use their ears to sort of like know if there's a wall near them. But almost any animal with ears and the ability to make noise can use echolocation. But there are a few really good examples that stand out because there are some animals that rely on echolocation to like see at all. Echolocation is the same in principle as active sonar. Animals will emit a sound and then use that echo that returns because sound bounces to gauge surrounding objects and their distance. Ranging happens through measurement of echo intensity and time delay, and the brain allows echolocation to happen. Breaking that down, what that essentially means is that in order to measure the distance and the direction that an object is relative to an animal using echolocation, the animal can measure several things with their brain. They can measure the echo intensity, which is just the volume, how loud the returning sound is, time delay, which is the amount of time it takes for the sound to travel. And also, I think I forgot to write or mention here, the concentration of the sound in one ear or the other. And the brain allows this to happen because not only does the brain allow the animal to build a picture of their surroundings based on echoes, the brain stem actually helps in dividing those neurological signals to distinguish between where the sound is between the right and left ears. So because the five senses are, neurological properties, there's a lot of brain chemistry involved in this. How the signals are sent to the brain, how an animal can make sense of the sounds that are being returned to them. And echolocation lets an animal see where it is going through navigation, and to detect the size of objects like animals and their direction, which is detection. So echolocation serves both the purposes of navigation and detection. The best examples are bats and dolphins. First, we're going to go over the example of bats. If you've heard the saying blind as a bat to depict something that can't see, or if you have a really bad eyeglass prescription, you'll understand likely that bats have very poor vision and they are nocturnal. They come out at night and have most of their activities at night, like hunting, moving around, mating. All of that takes place at night, and they sleep during the day, which is why it's widely known that bats stay in caves, because caves are very dark and they can provide the kinds of surroundings that we get from the night. And that makes echolocation a necessity, because in echolocation, an animal can understand their surroundings in the dark without having to see it. Do dolphins have bad eyesight as well? That's a good question. Dolphins do have decent eyesight, but below the depths of the ocean, light doesn't penetrate down there. So it's really hard to see deep in the ocean. It's actually very dark, which makes echolocation necessary for dolphins as well. And we'll get into that later. So echolocation lets bats see where they're going and their prey. So because a sound that's emitted from a bat bounces off everything that it's headed towards, it can also reflect off of things like moths flying in the air, insects, something like the side of a cave. Anything of any size, virtually any size, can be received an echo from in echolocation. Combined with the ability to fly, echolocation fills a unique niche for bats, and they can track and hunt prey while foraging and reach that prey. Niche is an ecological term, and it essentially describes the role that a organism plays or a species plays in its environment. Everybody here knows what a food chain, I assume, what a food chain is, I assume, but in like more complicated models like food webs, which describes what everything eats and gets eaten by, like taking into account all sorts of prey and predators. An ecological niche basically involves the role that an animal plays in their environment, what they do, what they hunt, what they get consumed by, what energy they consume, and what energy that they provide for other predators. So in other words, echolocation allows bats, by hunting at night, to consume things like insects that come out of those types. So the animals granted with the ability to echolocate are able to track and hunt prey during the night, which is by itself pretty unique. There aren't that many animals that are nocturnal in the way that bats are. Bats use ultrasound, which is a sound of very high frequency, and emit these noises through their mouths from their larynx. I believe that ultrasound in the context of like the medical field also entails like a way that scientists can or medical professionals can use the bouncing of sound off of a body to build an image of it. I'm not too sure about that, but what I do know is that ultrasound is a frequency of sound that's above what a human can hear. So it's too high pitched. A human's range of hearing for frequency is about 20 hertz to 20,000 hertz, or 20 kilohertz, kilo meaning thousand. Bats typically emit frequencies from 14,000 to 100,000 hertz, which is far beyond what a human can hear. And while 14,000 is within the range, they can get as high as 212,000 hertz, which is, 10 times higher than a human can hear. Bats are incredibly good at echolocation, and they can linear gauge elevation by their brains measuring echoes bouncing from the outer ear tragus. Like the structure of your outer ear, bats can use the reflection of echoes off of those fleshy parts of the outer ear to understand how high or low something is. They're very good at it. And they have very, very enlarged cochleas, which are internal ear organs that play a large role in here. Overall, echolocation allows bats to move to their prey, move to their destination properly without colliding with anything, find prey, forage and hunt, and see their surroundings in the air only. The sound travels through the air only. It does not penetrate through the ground. It largely does not penetrate into the water. Echoes would not return from the water back into the air to a bat's ear in a capacity large enough for a bat to effectively navigate through the water. And bats don't go into the water anyways, so that would be a useless functionality. Important to note that the speed of sound in air is 343 meters a second. That's relevant in the next few slides when it comes to understanding how echolocation works for dolphins. 343 meters a second translated over something like 780 miles per hour. Not sure, but sound does have a speed. It is the vibration. Sound is essentially a vibration that passes through molecules in the air. And sound actually travels faster in water, and we'll explain more about that in the next slide. But yeah, in summation, bats can use the echoes returned from sounds that they emit from their larynx in order to know how far away their surroundings are, what kind of surroundings there are. They can understand things like the size of prey, the density, and even things like the direction they're moving. The next example that we have is dolphins, and dolphins are highly adapted for echolocation. Bats do have very good ears, and they do lack good vision, which makes them good candidates for the development of echolocation in evolution, but dolphins are highly specialized for echolocation. We'll see about that in a moment. So in dolphins, they have special organ in the front of their forehead that looks like a bulge. That is called the melon. It's in front of the blowhole, which they use to breathe, and it's composed of fatty tissues and fluids. And the role that this melon plays as an organ is it focuses the sound that a dolphin emits when they're using echolocation. So it is a physical obstruction, but it helps to focus that noise when it goes out into the environment. Sound waves travel through the melon and then into the water, returning echoes as they bounce off surroundings and prey. So in practice, it works the same as any active sonar system, or like a bat navigates in the air by penetrating through the water and bouncing off of any objects in the distance or prey. Sound waves received through the lower jaw, which is also filled with fats and fluid, help receive the echoes that come back bouncing off of objects and surroundings. What's interesting about this is how you'll note that both the focusing organ and receiving organ are filled with fats and fluids, which play different roles. So in the melon, the fatty tissue and fluids actually help concentrate the sound and focus it into a more precise frequency, whereas when sound waves are being received through the lower jaw, they're being essentially refined by being absorbed or soaked up. After coming in through the lower jaw, or in other words, just the mouth, the sound waves will travel into the inner ear, then into the nerves, then to the brain, presumably dividing in the same way like through a brainstem in bats, so that dolphins can understand the direction of objects, how far away they're. Is the melon in the lower jaw hollow so it can contain fluids? Yes, they both actually are. The melon is a sac, sort of like, you know, a spleen or a gallbladder, and it's filled with those fats and fluids. While the lower jaw is a cavity in the dolphin's mouth. The brain translates the return sound into images. This is similar to the computerized methods that Sonar utilizes. They don't construct like a visual image of their surroundings, but returned sound into images is sort of a fancy way of saying that they identify the properties of their surroundings based on, the same thing as bats. The time it takes for the sound to travel back to them, the direction in which it passes into their ears, or I guess into their lower jaws and then into their inner ears. And as mentioned before, although dolphins is that how they research galaxies? Radiological astronomy is a thing. Sound would be highly inefficient because sound travels so slowly through air and also would not travel through space at all. You know how there's the widely held belief that like you can't hear you like scream in space? Well, that's because there's no particles in space to facilitate the movement of sound. The sound cannot propagate in space because there's no molecules for it to vibrate through. But instead, we will learn about things like radar and LIDAR, which they do use to research galaxies because light and radio waves travel much faster than sound. The reason why sonar in the form of echolocation is good for dolphins is the same reason why they can't see. It's because light doesn't travel well enough through water for the dolphins to be able to receive it through their eyes and see. So they need to use sound because sound works very well in water. Sound moves 4.5 times faster than it does in air. Well, radar waves move objects or do the bounce of the object. Radar waves move objects or do the bounce of the object. I'm not sure I understand that question, but what I think that you're saying is, well, radar waves are invisible to the eye and they penetrate through an object. So radar and radio waves don't physically move an object, or they just bounce off of the object. Yes. So do sound waves. Waves at virtually any time, even light. That's how you see. So sound moves very fast in water, 1,500 meters a second, which is 4.5 times faster than it does in the air. Because in a fluid, very, very basic level of chemistry. In a fluid, the molecules are much closer proximity to each other than they are in the air. Echolocation in dolphins can help them detect fish, which are prey, and objects actually as small as a ping pong ball from 100 meters away. That's very impressive because a ping pong ball is what, like 2 centimeters wide. So needless to say, echolocation and sonar are synonymous in this case, but both they work on the same operating principle, and that principle allows dolphins to effectively hunt without needing to see their prey. So next we're going to go over some of the evolutionary or the biological benefits and downsides to echolocation. So firstly, echolocation allows spatial sensing in poor-sighted organisms. Dolphins aren't inherently poor-sighted, but no organism could really see very well through dark water. If you've ever heard of bioluminescence, there are different approaches to animals being able to navigate through the water. Some animals can biologically produce their own light, like what do they call it again? Crawfish, I think. They can produce their own light through biological means in order to see, and dolphins use echolocation, as do some other whales, killer whales included. So echolocation allows spatial sensing in poor-sighted organisms because in order to navigate their surroundings and find prey, they need to be able to understand what is around them, how to avoid obstructions, how to effectively move towards their prey. And in this way, they enable an organism to hunt, navigate its surroundings, and understand its environment. Dolphins and bats alike move towards their prey without necessarily having to see them through echolocation, as they can as well navigate their surroundings and understand what's around them in their environment. As touched on before, through echolocation, our prey or predator is able to know the presence of the species sending the echo. That's a Good question, and we will touch on that in the next slide because echolocation, sounds produced by an echolocating animal can obviously be received by another animal that also uses echolocation. They to know the presence of the species, and so in short, yes, they can. Um, both prey and predators alike. Echolocation allows animals to navigate an area that their prey cannot. This sort of contradicts what I just said, but some prey can use echolocation, and so they can hear the echolocating noises made by an animal. They might not understand that they need to avoid it, though, which functionally cancels out their ability to detect the echolocation emitted by their predators. So anyways, moths, for example, are a main source of food for bats, and moths can't really navigate a poorly lit area that well. So bats can use this to their advantage and track them down without the moths being able to see them coming so that they can eat them. Likewise, not all fish are very great at echolocation, or hearing it, or sight for that matter. So dolphins can track them down more easily than the fish can see them coming to avoid them. Echolocation also, some recent studies say, could be more reliable to gauge distance, location, and the direction of motion of an object, size, shape, and other properties than vision, especially in the dark. So echolocation, because it's done at very high frequencies and the noises are emitted very quickly by an animal, they help an animal understand what direction their prey is moving in. And if it's moving away from them, if it's moving towards them, and they can lead their target if they know that they're moving, say, to the right. All sorts of things like density, size, and shape can be determined by echolocation. It's more than just a rough system of understanding that something is in front of an animal. And again, the theme of the dark. Sight doesn't work very well in the dark, so sound can take its place. Echolocation also provides a wider scope of surroundings than a field of view can, to the sides, above and below, and even behind. You can only really see what's in front of you. And while your eyes do provide you with a pretty good range of what you can see, for animals with a lower field of vision, echolocation can be advantageous because they can understand what's around them in a 360-degree range. They can understand what's to their sides, what's behind them, what's above, and what's below, and all sorts of directions. And echolocation can also allow rough communication. Obviously, bats are going to be able to communicate with each other. They're going to be able to hear each other's echolocating noises and high pitches because they're the ones that are able to receive them for the purpose of echolocation. They can serve rough communication purposes. Obviously, echolocation can never serve as a substitute for spoken language like in humans, or even like body language and like territorial behaviors in other mammals, but it can serve as a auditory indicator. And some downsides of echolocation. Echolocation has a limited range. So sound can only travel so far, and the farther away sound travels, the weaker the echo is going to return. Echolocation doesn't have that great a range compared to light in a perfect environment. So like if you were just, let's say, outside, you would be able to see a way farther distance than a bat could detect with echolocation. And dolphins actually have a much better range than bats do. Because again, sound travels much better in water than it does in air. So another weakness of echolocation is that information can be compromised, because again, information is a function served by echolocation. It can be intercepted by other animals that can hear the echolocation as well. So an animal, while in the process of hunting, could give away its position to a predator. Damage and compromise by noise pollution. Humans make a ton of noise in the modern environment. We're always constructing things, making noise, even just speaking could adversely affect echolocation, because echoes can't be precisely detected if an environment is very loud and noise polluted from multiple sources in multiple directions. So a bat wouldn't be able to distinguish what echo is returning from the body of a prey if hundreds of other sounds are coming in from like all sorts of other directions. Essentially, it's just sound sensitive. It would be akin to like if you were trying to hunt, somebody shining a flashlight into your eyes from multiple different directions while you were trying to see one thing. For bats, this can include human activity and other animals in its presence using echolocation. And for dolphins, whales, and other water-dwelling echolocating animals, ships can pose huge threats to echolocation and hunting. Cruise ships, any sorts of boats that use motors that make a lot of noise in the water can very quickly reach dolphins and disrupt their ability to echolocate. A side note is that sonar used by the military or civilians can hurt and kill dolphins who can't handle the extremely loud 230 decibel sound waves that travel very fast underwater. The military is a huge proponent of sonar, and since they send out sound waves that are like twice as loud as a rock concert, they can really damage and hurt animals that are attempting to use echolocation. And lastly, we have the development of sonar from the example of nature, how echolocation led to sonar. In World War I, which lasted from 1914 to 1918, submarines became a threat to ships in the water as they could not be visually detected. They remained underwater and invisible to sailors on the deck of a ship. In 1915, in the middle of the war, Paul Langevin invented one of the first practical sonar devices called echolocation to detect submarines, translated from French, I believe. By 1918, which was kind of too late to make a real impact on the war, but it was revolutionary in the scientific community nonetheless, active sonar was developed, working on the same principle as echolocation, sending a sound and then receiving. Man-made sonar concepts today are influenced by these same principles put to use by dolphins. For example, scientists at the University of Southampton developed a new kind of underwater sonar device that can detect objects through bubble clouds. Dolphins have the ability to penetrate things like dolphin clouds with their echolocation frequencies. And because regular man-made sonar would be blinded, since it still works in a different way from echolocation, rather than sending out one noise, it sends out many precise beams of noise, if you will. Regular sonar would be normally blinded by bubbles, but with the help of studying dolphins and borrowing the frequencies that they use, sonar has been invented that can penetrate through bubbles and be able to see. So this has been a lesson essentially on how navigation systems take examples from nature. In the future, we're going to go into depth on 3 topics, and those are radar, sonar, and LIDAR, which are 3 of the most lucrative technologies in the field right now, and they are very advanced. So thanks everybody for coming, and I'll see you all.
Bye.